In this video, you'll learn how to create multi-agent systems using reinforcement learning in Python. Master the foundations of designing and implementing multi-agent environments, crucial for developing complex AI systems capable of cooperative and competitive interaction. Welcome to our deep dive into the fascinating world of multi-agent systems using reinforcement learning. Did you know that multi-agent systems are the backbone of complex AI applications like autonomous vehicles and smart grids? Today, we're going to explore how these systems work and why they're so crucial in the AI landscape. We'll cover everything from setting up your Python environment to implementing communication protocols between agents. By the end of this video, you'll have the foundational knowledge to start building your own multi-agent systems. So, make sure to stick around, and don't forget to engage with us in the comments section with any questions or insights you might have.
To kick things off, let's set up our Python environment. First, you'll need to have Python installed on your machine. I recommend using Python 3.8 or later for compatibility with most libraries. Next, create a virtual environment to manage dependencies for your project. This helps keep your projects isolated and organized. Once your environment is ready, install essential libraries like NumPy, TensorFlow, and OpenAI Gym. OpenAI Gym provides a toolkit for developing and comparing reinforcement learning algorithms, which is invaluable for our multi-agent setup. Python is popular in the AI community for its simplicity and powerful libraries. However, be cautious of common setup pitfalls like version mismatches. Once your environment is set, you're ready to dive into designing your multi-agent environment.
Designing a multi-agent environment is a critical step in the development process. Let's start by understanding the interaction between agents and their environment. Each agent perceives the environment through a set of states, selects actions, and receives rewards as feedback. Defining these states, actions, and rewards is essential for shaping agent behavior. When designing for multiple agents, consider how they interact. Are they cooperative, competitive, or a mix of both? Using OpenAI Gym, you can implement your environment by extending the end class and defining the step and reset functions. For instance, in a predator-prey scenario, predators might cooperate to catch prey, while prey competes to escape. These interactions are pivotal in creating realistic and complex multi-agent tasks. Communication is a cornerstone of effective multi-agent systems. Imagine a team of robots coordinating to move a heavy object without communication. This task could become chaotic. Various communication protocols exist, ranging from simple message passing to complex negotiation strategies. In Python, you can implement basic communication using shared variables or more sophisticated methods like sockets or message queues. One challenge is ensuring reliable and efficient communication, especially as the number of agents scales. In real-world scenarios, such as autonomous vehicle fleets, effective communication ensures safety and efficiency. By implementing a robust communication protocol, your agents can synchronize their actions and achieve common goals more effectively. Training agents simultaneously can significantly enhance the learning process in multi-agent systems. By training in parallel, agents can adapt to each other's strategies in real time, leading to more robust solutions. In contrast, sequential training might lead to overfitting to specific behaviors. To implement simultaneous training in Python, utilize multiprocessing or threading to run multiple agents concurrently. This approach requires careful management of shared resources and synchronization. While parallel training can be computationally intensive, the benefits often outweigh the costs, especially in complex environments where agent interactions are dynamic and unpredictable. In multi-agent systems, agents often need to cooperate or compete to achieve their objectives. Understanding the balance between these dynamics is crucial. Cooperative scenarios require agents to work together towards a common goal, which can be encouraged through shared rewards or by designing tasks that necessitate collaboration. Competitive scenarios, on the other hand, involve agents vying for limited resources or objectives, often leading to adversarial behavior. Balancing these dynamics requires careful task design and reward structuring to ensure that agents learn to cooperate when beneficial, while also competing effectively when necessary. Real-world applications, such as trading agents in financial markets, often exhibit a blend of cooperation and competition, highlighting the need for flexible and adaptive strategies. Evaluating agent performance is a vital component of developing successful multi-agent systems. Various metrics can be used, including task completion time, resource usage, and reward accumulation. Continuous evaluation allows for the detection of performance bottlenecks and areas for improvement. Tools like TensorBoard can help visualize learning progress and diagnose issues. One challenge in evaluation is accounting for the stochastic nature of multi-agent environments, where outcomes can vary across runs. A case study involving a multi-agent navigation task can illustrate how evaluation metrics are applied to assess agent performance and guide further development. As with any complex system, multi-agent reinforcement learning comes with its own set of challenges. Common pitfalls include overfitting to specific agent behaviors, inadequate communication protocols, and poor scalability. To avoid these issues, it's important to follow best practices such as designing scalable architectures, ensuring robust communication, and continuously evaluating and adapting strategies. Real-world examples, like failures in autonomous vehicle coordination, highlight the importance of thorough testing and validation. By adhering to these best practices, you can develop more resilient and effective multi-agent systems that are capable of tackling real-world challenges. We've covered a lot of ground today in our exploration of multi-agent systems using reinforcement learning. From setting up your Python environment to designing complex agent interactions, you're now equipped with the foundational knowledge to start building your own multi-agent systems. Remember, the key to mastering these concepts is practice and experimentation. Join our community by subscribing to our channel and participating in discussions. We'd love to hear your feedback and any questions you might have. Stay tuned for more content on advanced AI topics, and don't forget to hit the subscribe button for updates.